All right, we're back recording. All right, we got this last set of posters, the purple banners, so rotational motion, rotational dynamics. Right now, rotational kinematics, we were looking at the other day. So those aren't gonna. Right. Here we got center of mass. All right, center of mass. So this gold box says that center mass is, think of it being like a weighted average, right? So the sum of mass times position all divided by the sum of mass, right? So I got an example here with, let's say I got a couple masses, mass A, mass B. Let's say they're stuck together on a stick, like a very lightweight stick, right? So like this dashed line, maybe it's like a meter stick with negligible mass, right? Maybe you want to balance that on your finger. Ooh, that would balance probably about this dot here, right? Center mass, right? But how do you find that? Also, if you threw that through the air, it would also rotate about that point, right? So, okay, mass A times position A plus mass A position B, all divided by, sum of masses. Yeah. So like the more massive MA is, the center mass is going to kind of shift that way, right? Something like that. Now, are you going to solve exactly that on AP exam? Probably not, but AP does like center mass type questions. So let me flip my screen over and show you guys some more AP style center mass question that came across. Right, so I have a couple of notes from earlier today, so just to save some time, just throw this up here. So one could be, let's say like a grenade, right? Say you take a grenade, throw it through the air, and if it doesn't explode, or you just like throw a regular baseball, maybe it lands like right here. Right? Okay. Now I go back and throw, let's say the grenade explodes, pow, like right here, and it explodes to like 10 different parts. Like, wow, I get like a shower of grenade parts, right? Well, guess where the center of mass lands exactly? Ooh, as if it had never exploded at all. I'm talking about the center of mass of all the little bits, right? So you get like that. If you ever see a collision, maybe blocks are in motion, and you have like the center of mass of those blocks, right? Then you'll never know when the collision happens if you only focus on the center mass. Right? Kind of the exact opposite thing here, right? If you just focus on the center mass, you would never know when it exploded because the center mass just does its own thing, right? Right. Another example AP likes to do that kind of involves the center mass tie-in is, I've seen this question a few times. There's like a guy standing on a floating block of wood. I guess his block of wood, it's floating in the water. I got like an island over here with a tree on it, so it can measure velocities with respect to like the shore, right? Okay. So this guy's standing on this block of wood. Well, if I treat the person wood system as like a closed system, right, I could do that. I'm ignoring drag force from the water. That's a kind of a huge simplification, but assume there's no drag force from water, right? If this guy walks to the right, guess which way the plank moves relative to the outside world? Gets kicked back to the left, right? And guess what happens to the center of mass between the person and the wood? Stays exactly where it always was. So the guy moves to the left, block moves to, or the guy moves to the right, the block moves to the left, but the center mass just stays right put where it is. Right? Hey, what if this thing's like floating at 3 meters per second to the right? And this guy moves to the right, so he's kind of kicking the block wood back, right? If you just focus on the center mass of the system, right, you would never know where this guy's like walking back and forth, right? It's just like always drifting to the right, 3 meters per second. Right? So some version of that question, good chance one of those you guys will see on the AP exam too. Right, so you guys good with the center mass type question, Mike? Right, moving on. Ooh, stability. I don't think AP will ask this, but here's a little bit extra. Right? You guys are going to see a little bit extra stuff today. Right? So what makes something unstable, neutral, or stable equilibrium? Right. So here's like definitions right now. If something undergoes a small displacement and then it like takes off, accelerates further in that direction, okay, well that's unstable. There's a couple of picture examples. If you give something a small push and it sets up a new equilibrium, we'll call that neutral equilibrium. There's a couple examples. Right? If you give something a small push and it goes back to its original state, right? Like you push on this pyramid and it just goes back to where it was, or I push on this picture frame, it goes back to where it was. That makes it stable. Rotational inertia. So the first few months of this class, inertia, we could just measure by the amount of mass, right? If it's like 3 times the mass, it's 3 times the inertia, right? You push on something with some force, how much does it accelerate? Oh, inversely proportional to the mass, how much inertia, right? But when we get to this rotational dynamics, it's not just how much mass, it's where that mass is located. So this is the sum of mr squared. So here's an example. So you got a couple masses taped to meter stick, just like here, these meter sticks over here, right? Passes around class a couple times, right? Let's say the meter stick itself is negligible mass. We're just focused on those red point masses. So I got mr squared plus this mr squared. Hey, that makes 2mr squared, right? The plus, that's what the sigma is, right? You're adding up. Right? What if you shift it 3 times further away from the center? So that's m times 3r quantity squared. So it's like 9mr squared, right? And then times 2 because of this one. That's like 18mr squared. Is it? So by pushing the masses 3 times further away, you get 9 times the rotational inertia, right? 9 times as difficult to change a state of motion, or rotational state of motion. Right? let's look at a big old table. So I know for a single point mass, it's like mr squared. Right? We also had a whole lab. It's one of these slides coming up. Can I show that too, right? Mr squared. What about for other shapes? Well, a ring rotating about this central axis. Okay, that's just like a bunch of mr squared. So effectively, it's mr squared aggregate, right? But what about like a turntable? If you take the solid cylinder and turn it vertical, that's your turntable, right? Well, a lot of that mass is distributed closer in, so it'd be less than mr squared, and it ends up being 1/2 mr squared mathematically. Right? And okay, so we've got all these other objects. Okay? Let's compare these two: the bowling ball to the basketball. Right? So okay, obviously the mass and the radius matter for something, but what about like the distribution of those masses? Right? The basketball, the fact that it's like a spherical shell, right? Like all the mass is toward the outside, that's going to have like a greater inertial effect compared to the bowling ball, where more of its mass distributed closer to the inside, right? And you see that here in this fraction: 2/3 versus 2/5. 2/3 like 0.67, 2/5 like 0.4. Right? You guys see that? Right? You would not be expected to memorize that either on this midterm or for the AP exam. If AP wants you to do something with this, they would have to give that to you. Right? They'd have to tell you, list that out. Right? Parallel axis theorem. Okay, here's one that I think is nice to know. AP will not ask you about this, but I'm told that they will starting next year. So if you're competing against, like the slightly younger cohort, for like engineering jobs, might want to know this, right? So the idea is, what if you are revolving around an axis that's not one of the predefined axes according to this table, right? Like I dashed off some axes that align with these rotational inertia values, right? For example, if this ball is like revolving around this axis over here, which is parallel to the axis that it could be spinning about, hence parallel axis there, right? Or what if it's rolling along the floor? Maybe that's a more common example, right? It's not actually rotating about its own center, it's rotating about this pivot point down here, right? So you take the value straight off the table. That's what I naught is, right? Straight off this table, right? And then you add md squared. And if it's rolling on the floor, that distance would be its own radius. So you can sum it up like that. So rotational inertia rolling on the floor is more than just spinning about its own central axis. Like if you spin it on your finger, that's 2/3 mr squared. Rolling on the floor is like 5/3 mr squared for a basketball. Okay. Right. Torque. Okay. So now we're back to something you definitely will see on the AP exam, right? So torque is R cross F. Cross means you only multiply the perpendicular components. So R, F, and then sine theta, right? Now, careful though. I've labeled this blue theta in a way that aligns with the definition, right? R, F, sine theta, right? You might possibly be given an angle relative to not the radial orientation, but to the perpendicular, like this angle right here. Well, let's call this like beta, right? Because if this is angle beta, and you're given that, then this would not be RF sine beta. This would be RF what? Cosine beta. Right? It goes from sine to cosine, because theta and beta would be complementary angles, wouldn't they? Right? So careful about that. Torque is also I times alpha. I've got better examples of that coming up later. Okay, so you guys go with torque. Right? So turning the nut with the wrench, opening the door, push on the handle. Okay, right hand roll. Here's another one that not quite AP's perspective. AP's not going to ask about this, but if you go hard science engineering in college, you're going to see this, right? This is a mathematically better way to describe torque, right? Like in this class with torque, we're going to describe clockwise versus counterclockwise. Like it looks like from our point of view, we're trying to rotate this thing counterclockwise, right? But if you're standing on the opposite side looking this way, then you would say the opposite, right? So which way is it going, clockwise or counterclockwise, right? Right. So on AP, you would just say counterclockwise, call it a day, right? But like in three spatial dimensions, what way you can deal with this mathematically is to open up a z-axis, right? So now we have an xy plane down here, but now this is third axis you can define it about, right? And then you can do crazy stuff mathematically with this, right? So here's cross products solved with matrices. Okay, you're definitely not going to be asked this on either this midterm or the AP exam, but go to college, good chance you'll see this. You can do crazy cross products in 3 dimensions, right? This rich oriented like 3-dimensional space, right? Something like that. I, J, and K are the X, Y, and Z axes. Okay, all right. So a little bit different view. So I just want you guys to be aware that's there. Learn matrix math if you want to do some really fun 3-dimensional math. Okay. All right, rotational inertia lab. Here's the last lab that we did. Like, what's the rotational inertia of this crazy PVC pipe system? If you grab that central axis and rotate it, I feel a little bit resistance to change of motion, right? That was a tiny bit of frictional torque, but that's not the main drive. So there's definitely some rotational inertia, right? How much rotational inertia? Well, this could totally be experimental design FRQ. They could say, like, how would you set up this experiment to determine that, right? And well, you just write exactly what we did. So let's step through that process. So if you attach a lab weight here and on the string that's now wrapped around the central axis, right, that's going to cause a torque, R cross F. Now it's a small radius. I think it's about a centimeter or so, right? Cross F. And the F is the tension of the string. which, if you remember, is a little bit less than the weight of this hanging lab weight because of elevator physics. If it's accelerating down, right? Although it didn't make a huge difference, the tension was almost the weight. Right? Okay, so we got some r cross f that results in I times alpha, right? So the angular acceleration of this speeding up spinning is also equivalent to this linear acceleration divided by this radius, if you remember turntable physics, right? That connection, right? Thinking about it right here. Okay, so put it all together, you can solve for I. I is then the slope of torque versus angular acceleration, right? Now I'm saying the slope of that graph because that graph also had a vertical intercept, which represented frictional torque. You guys remember that too? Okay. All right. Equilibrium. Right, so for this class and also for AP, probably just focus on that gold box right there. So maybe you'll have like a 2D plane. The forces have to zero out in each direction, and then the torque also zeroes out. Right, so you have those three conditions now for equilibrium. Right, now if you go like full engineering in college and you're designing some giant 3D static structure, then you'll probably have to open up all 6 of these conditions here. Think, okay, now I've got 3 dimensions. Right, okay, so everything comes to 0 that way. Right. Oh, seesaw equilibrium. You guys had a 2-day torque lab, and this was day 1. So we're zeroing out the torque. One thing you can use this for is to solve for unknown weights, right? And I've done this a number of times, right? Say I pick up some weight, I wonder what's the weight of this thing. So I'll go grab a meter stick, throw the meter stick out, balance it at the 50 centimeter mark, maybe like throw a pin or something acting as a pivot, right? Okay, so it's all balanced. I'll take a known lab weight. Say like I'll take like your 5 Newton weight, for example, like stack it there. And I'll take my unknown weight, stack it up, and then slide it around until it balances, right? And where it balances, I can say the torque sums to 0. And you can say the counterclockwise and the clockwise torques balance, and you can very quickly solve for that weight, right? That's the exact same principle that a triple beam balance uses, right? You guys remember you have the digital scale, but you also have that triple beam balance, right? Now, the digital scale works off forces. So if you took that to the moon and used it on the moon, well, it'll give you the wrong reading for mass because it's really reading the weight and saying, well, divide by Earth gravity, assuming it's okay. But if you took a triple beam balance to the moon, would that give you the correct mass of the object? It would, because there's less weight, but then less counterbalance. So the gravity field ends up canceling out, right? Yeah. So as long as you have gravity, it doesn't matter how strong it is. Okay, so got that. Then you guys did the scaffold version of this. I think I want to change that title to scaffold. Right? I think I told you guys the story. Paul Hewitt, before he got into studying physics, at one point he was a sign painter. He's walking back and forth on the scaffolding, held it by a couple of ropes. And he goes, hey, if I like walk towards the right, I think the tension the one on the right is increasing and the one on the left is decreasing, right? So how much tension in the ropes depends on not just how much weight you have standing on the scaffolding, but also where you're standing, right? Right, so I'm thinking of a couple of equilibrium equations, right? The forces sum to 0, and since it's all vertical forces, I can just take one equation out of that. Right? Now, if your goal is to figure out what are the 2 tensions, the left tension and the right tension. Let's say you know the weight of the scaffold, weight of the beam, and also the weight of like the person walking back and forth. Right? Then you have 2 unknowns, so you can't determine both tensions just from this equation alone. Right? There's not enough info. You also have to bring in location, and that involves torque. So I'm summing the torque to 0. And when you guys did this lab, I had to sum the torque about 2 different locations and show you it zeroes out either way, right? There's no single point that's special as the pivot point, but sometimes there's a mathematically convenient place to choose as the pivot point perspective. So in this equation setup, I know I picked this far left end point right here as the pivot point, right? You can treat this like the door hinge. And I know I did that because I see right here, here's my r cross f, right? Radial distance is 0 meters away from that force itself, right? It's kind of like pushing on the door hinges of a door will never turn the door, right? And the mathematical advantage of doing that is that it zeroes out one of my 2 unknowns, right? If I don't know the left tension and the right tension, then this one just zeroes out. Therefore, I can immediately solve for the other tension with just a little bit of algebra, right? Right? And then figure out left tension maybe from this other one. There you go. Torque, right? Okay, there's your torque table for the seesaw version. There's torque table for the scaffold version, right? And of course, the back of my room in the middle, I got exactly that set up. You can see it right there. Okay. Ooh, this one right here. You guys know this one. For sure, you're going to get some AP questions about this in May. So what if you got a turntable, you wrap a string around it, and then you pull with a constant force? Well, that constant force at this constant radial size, and it conveniently always sets up at right angles, right? No matter how you pull a string, right? It produces a constant torque, right? R cross F. Now that R cross F, okay, here's where the other perspective of torque opens up. The sort of Newton's second law, but in a rotational sense, torque equals I times alpha. That's analogous to F equals ma, right? So that's going to cause us to speed up spinning. If you pull with a constant torque, it's going to cause us to speed up spinning, right? Speed up spinning is called angular acceleration, and you can quantify that in radians per second squared, right? Now, how much that is also depends on the rotational inertia of this disk, right? Now, here's where you could calculate this from scratch. Let me go back a few slides to, how far back is this? Okay, this rotational inertia table. You can say, well, if that's a solid cylinder, which a turntable pretty well is just this, turn vertical, right? You do 1/2 mr squared. If you know the mass of the thing and the radial size of the thing, you could calculate that. Again, you wouldn't be expected to memorize that. If AP wanted you to do that, they would give you this expression so that you could say, okay, 1/2 mr squared for this turntable looking deal, right? Right. Then you can solve for alpha, right? So you say R cross F equals I times alpha. There's your two perspectives on torque. If you can identify R and F and I, you can solve for alpha, right? Usually AP gives you I if they want you to do that calculation, right? You could take this another step. You could say, well, now if you know angular acceleration, you could be asked a kinematic question like, if you pull for some interval of time, like 5 seconds, how fast is this thing rotating? That's omega in radians per second, which may be only true at one instant. I mean, if it's speeding up spinning, then any particular speed, it's only true for one instant, right? But that would kick over to a kinematic type question. You could pull up those rotational kinematic formulas, right? Like theta equals omega naught t plus f alpha t squared, and a couple other ones up there, right? You do something like that. There's this other aspect, angular momentum. So angular momentum we're calling capital L. That's I times omega. That's kind of analogous to P equals mv, right? And angular momentum is also conserved. Ooh, I remember this sure does look a lot like a gyroscope. Get a gyroscope spinning, right, or a top, or spin a coin. Remember, once maintain its position, right? Maintain that angular momentum, right, if it's spinning, right? So a lot of things in that picture right there. Definitely know that picture. There's a lot that ties into that. Right? These two graphs correspond to, it could be corresponding to that story, right? So here's how. Suppose you apply a constant torque for some time interval, right? Well, a constant torque, which is what you're seeing here, that's what this black line is, right? Means that it's speeding up spinning. So there's an angular acceleration, which means it's spinning faster, faster, faster. Well, it's faster, faster, faster. That means more and more and more angular momentum. That's like you're opening up this rectangle, bigger, bigger rectangle, the more time you apply that torque for. Is that right? And then what if you made a graph from the angular momentum point of view? Okay, well, it's this graph on the right. Angular momentum as a function of time is, of course, increasing. It's increasing at a constant rate because as you make this rectangle wider, right, that's increasing constant rate. Therefore, L versus T increases at a constant rate. In fact, the rate it's picking up is equal to torque. The slope of L versus T is tau, torque, right, which is this right here, right? So again, there's like a calculus connection. The integral of tau versus t is L. The derivative of L versus t is tau. Or something like that. Right? Yeah. Okay, you guys get there? Your last AP classroom, you guys saw a few of I think there were a few questions that tied to these two graphs, right? I remember one of the questions being, what if there is not a constant torque, but what if, here, going back to this story, what if you pull with a harder and harder force, right? And you have like an increasing torque. So now these graphs are going to look different, right? Guys, if you have a linear torque, do you guys remember what angular momentum looks like? It's like a parabola shape, right? It would be, right? That was a little trickier, right? Right? A lot more likely that you'll get a pair of graphs that look like this, right? And again, like if you know one of these, the other becomes pretty well locked in place. Right? Okay. Hey, spinning a basketball, right? I can think of a couple ways to solve this. One way could be kind of like the way I took you through before. You could solve for alpha and then put in the time interval and go back to kinematic motion, right? But here's the way that kind of bridges over a couple of those steps, right? You can go through angular momentum, right? So right, there's two different ways of solving, and they're not super dissimilar, but here's a little bit faster. Right? You say torque times time is the change in angular momentum, right? That's the same thing as the area of this green rectangle, right? Torque times time, right? So Newton meter seconds could be equivalent to this, right? Okay. Okay, so if I apply a force at the edge, suppose you, bam, apply a force at the edge of that basketball. Okay, well, for R cross F, there's your torque, right? That delta T, that time interval, might be like a fraction of a second, maybe like 0.1 seconds, just bam, right? And that's going to get this basketball spinning. How fast? Well, let's see. I know torque times time gives you angular momentum. I know angular momentum is I times omega. I could go to that rotational inertia table and say for a basketball or a spherical shell, it's about 2/3 mr squared, right? Okay, here's omega. That's the end goal, is to solve for omega. How fast, how many radians per second is that thing spinning? Due to like bam, applying that force by that time interval. Right? And so end of the day, we're going to get this right here. So how fast is rotating in radians per second? See, the more force, the faster it's spinning. The more time you apply that force for, the faster it's spinning. The more mass, the slower it's spinning, because more inertia. Right? And then the more the radius, there's kind of a trade-off effect, because more torque, but then more angular momentum, inertia, right? Rotational inertia. So at the end of the day, larger radius corresponds to spinning slower. Right? You guys said too, inverse relationship. Right? Now 3/2 I put in orange because that applies specifically to a basketball. Guys, what if you replace that basketball with like a foam ball, which was solid all the way through? Well, what would change is just the orange stuff, right? That 2/3 would become 2/5, just a different value from that table, right? Rotational inertia table. And then the end result would be 5/2 FT over MR. Okay, you set? So you guys could solve that. I think that would be a pretty decent FRQ right there. If you could ask that, that would be good. 7 FRQ. You could ask that. Again, it's it kind of goes hand in hand with that picture right there. When you just turn that disc into a basketball, it's not crazy different. Right? Really similar looking story. Right? Ooh, figure skater. So here's a really good conservation of angular momentum example, which is exactly what this box says on the right. Right? Sum of angular momentum initial equals sum of angular momentum final. Right? Now remember, angular momentum is conserved, kind of like linear momentum is conserved. Right? Linear momentum we were using for collisions. Angular momentum conservation you could use for exactly this, right? Figure skater. Okay? So that's I times omega. So I times omega before equals I times omega after. Right? We got mass distributed far out, and then pull your arms in. Right? So you'll spin faster, faster, faster. Right? So you guys know that. Okay, so you guys see the whatever factor I decreases by, omega is going to increase by the same factor. Right? Something like that. I got a follow-up question for you guys. Which of these pictures, the left picture or the right picture, which of those pictures is there more kinetic energy, or do they have the same kinetic energy? Right. Let me see, show hands. So your three options are, so who has more kinetic energy? Is it the picture on the left, picture on the right, or are they identical kinetic energy? Okay. How many of you guys think the picture on the left is more kinetic energy? Nobody says that. How many of you guys say the picture on the right is more kinetic energy? Yeah, okay. And I'll tell you guys from two different points of view why there's more kinetic energy on the right. Right? One is that, guys, if you're spinning and you pull your arms in, doesn't that take some effort, like force times distance? Ooh, right? Hey, that's like doing work. That's converting energy from your muscles, like stored chemical energy from, into mechanical energy, right? So you're kind of adding mechanical energy into the system. Now you're not creating it; it's coming out of your muscles, but that's like adding mechanical energy to the system, right? Another perspective is the equation. Guys, what's the equation for rotational kinetic energy? 1/2 I omega squared, right? Okay, so remember a minute ago I said clearly here the proportional decrease in I is the same proportional increase in omega, right? Well, if you're looking at the equation 1/2 I omega squared, the fact that omega is being squared, it's like that increase ratio gets like double counted, right? Okay, so if it's like 1/2 and then times 2, okay, so that 2 is getting squared for kinetic energy, so kinetic energy goes up. Keep track of that. Ooh, angular momentum for a point mass. So I see regular momentum for a point mass, just mass times velocity. Now, what if it's like a swivel stick, or your recent quiz, there was like a paddle wheel, right? And then how fast does the paddle wheel get rotating, omega? Maybe I should extend this poster and also include something like that too, right? Because that's what that would be, right? I can say L equals I times omega. So post collision, there's some rotational inertia. Now, if it's just the stick itself, suppose this ball like boing bounces off, then just the stick itself is set into motion, or the paddle wheel could be set in motion, right? Has some rotational inertia, right? If it sticks, like collides inelastically with stick, then you also have to include in the rotational inertia, you have to add the mr squared from the point mass that's also stuck on there. That's even more inertia, right? That's going to send it into like some omega. So you can say mvr equals, and then I times omega. As long as you have the correct I, you'll get the correct omega. Radians per second rotating, right? Almost guaranteed AP is going to ask you that question right there. I bet that's going to be one of your multiple choice questions in May. Right, that right there. Okay. Ooh, ball rolls down an incline. Right, so I have 2 slides for this. 2 slides. different points of view. And the question is the same for both. What is the linear speed of, in this case, a basketball at the bottom of the incline? And notice they're the same answer, right? So they get to the same, okay, but you guys have seen that all over the place in physics. A lot of times there's multiple ways to solve things, but if you do it correctly, you should get the same answer regardless of how you solve it, right? Now, here's the hard way to do it, and here's, well, what I think is the easier way to do it, right? So let's start with the hard way. The hard way is setting up a free body diagram and going through torque and angular acceleration to ultimately solve for the speed at the end, right? How do you do that? Right. Well, there's three forces on this basketball. The normal force from the surface, which doesn't really cause any torque, so that one doesn't really make any difference to the answer, right? But these other two forces, the weight mg going straight down from the center, and the friction force. And notice I labeled the friction force at the surface, which is important for torque because you need forces in different locations to set up a torque, right? R cross F, the radial arm would be like the radius of the ball, right? So those two in conjunction with each other, and you need a frictional force to cause any torque. Guys, if you had a air hockey table with no friction on it, would this ball even rotate? No, it would slide down without rotating, which would look weird, but that's what it would do. Yes, and usually the textbook says rolls without slipping or rolls without sliding, right? Something like that. So this friction is specifically static friction, right? And it's also a conservative force, which means that it doesn't take energy out of the system, right? It just induces rolling. Okay, so got that. So here we go. Torque equals, okay, so mg r sine theta, it works out to, I'll let you guys kind of think deeply about that. Can you figure that out? But it's basically r cross f, right? Okay. Torque also equals I times alpha. So now we can equate those two things. Here's your mg r sine theta that induces rolling, and here's what it causes, I times alpha. Oh, but alpha could be a over r, right? I made a kinematic substitution from this line to this line. If you guys remember that third kinematic equation, v final squared equals v initial squared plus 2ax. Okay, well, if it starts from rest, all right. At the end of the day, acceleration is equal to v squared on 2x, and then the x here is L because length is gone. So there's v squared over 2L. That r is that r. Right? Also did a substitution for I. Now for a basketball, okay, you do have to bring in parallel axis theorem, like the fact that the ball is actually rolling about its edge point. Right? This is only for this method, not the next slide. This is only for this specific method. Notice it says 5/3 rather than 2/3 for m squared, right? Right. That comes from parallel axis theorem. All right, so here's the speed of the ball at the end. Right? Guys, notice what matters and what doesn't matter for the final answer. Right? So I see a square root, I see a fraction. That I bet that 6/5 only applies to like a basketball or spherical shell. Right? The gravity field matters. This height change matters. H. Could you substitute in L sine theta for H if you had to? You might have to do that. Right? Does the mass of the basketball matter? It ends up canceling out. I see it in the middle, but it cancels out by the end. Does the radial size of the basketball matter? Also cancels out. Interesting. Right? Next slide. Here's the same question with the exact same solution, but I think this is an easier approach. It's all potential energy at the top. It's two kind of kinetic at the bottom. You got translational kinetic and you have rotational kinetic. Now that I is related to that m. Oh, notice I did just the regular 2/3 mr squared rotational inertia for the ball, right? As if it's rotating about the center. You get different perspective. You're allowed to do that for this version, right? And omega is v over r, substitutes in there, get the exact same answer. Right? Again, the mass and radial size of the ball cancel out. The fact that it's a spherical shell, it always have the solution. Right? If it's a solid ball, you guys solved a solid ball, I think, on your last quiz. I bet you got something square root of something gh, right? So some root of that, right? Finally, let's have a roll race. Got this incline with some static friction, with the exception of I have one frictionless lane, just to let an air hockey puck slide down with no friction, just for comparison. Now that's going to beat everything because all these other guys, some energy goes in making it rotate, roll, right? Right, and they finish in this order. Like the more the mass is distributed towards the outside, is going to lose the race. Like the ring is going to lose, right? Because mass is all on the outside, right? Right. Hey, let's see if you guys are following. What if you have a race between a solid bowling ball and a solid marble? Does the bowling ball win the race? Does the marble win the race, or do they tie? They're going to tie because they're both solid spheres, right? And again, the mass and radial size I'm canceling out. Okay, something like that. All right. All right. So you guys get there? All right. All right. Well, we got 30 seconds to the bell. So if you guys have any questions, let me know. But otherwise, let's get a pause point. Monday's a regular school day, as far as I know. So yeah, hope you guys have a good weekend. See you guys then. And if you want to do quiz corrections, bring that to me next few days.